Swayam Prabha. Digital India. Educated India.
Dear all, now we are going to continue the concept of congruences referred by Song, number theory by Song. Then we have to start with the basic concept and properties of congruences. First, we recollect that congruences, let A be an integer and n a positive integers greater than 1, we define A modulo n to be the remainder R. When A is divided by n, then the remainder R can be expressed A modulo n or A minus ceiling A divide n into n. So, we may say that R is equal to reduced modulo n. So, this is the statement written by that book, and then I took from that and corresponding how we can define in another way of writing the congruences. Now, shall we move to some example. The following are as examples of modulo n. If you take a number 35 under modulo 12, 35 divided by 12, the remainder is 11, therefore 35 is identically equal to 11. Similarly, if you take minus 29 and then divided by 7, then we have the remainder is 4, therefore we can express minus 29 under modulo 7 is 4. And 3210 under modulo 101 you take it, and then the remainder is 79, therefore 3210 is identically equal to 79. And 10412 that is 1412 power 13115 under modulo 12349 is identically equal to 1275. So, this way we can express the modulo of one number to the another number. Now, we have a definition. Let A and B integers and n a positive integers. We say that A is congruent to B under modulo n, denoted by A is identically equal to B under modulo n. So, we can write in terms of the divisors, if n is a divisor of A minus B, or equivalently if n divides A minus B. Similarly, we write A is not equal to B under modulo n, then it is said to be incongruent of A and B. So, this way we can express the congruences of one number to the another number. Now, we will continue the concept of congruences. If A is not congruent or incongruent to B modulo n, or equivalently if n does not divide A minus B, make a note of that. If n does not divide A minus B. So, clearly A is identically equal to B under modulo n, represent A is not identically equal to B under modulo n, we can write A can be expressed Kn minus B, or A is not equal to Kn minus B. So, for some integer k, so the integer n is called the modulus. So, this way we can write what incongruent of one number. Clearly, A is identically equal to B under modulo n if and only if n divides A minus B, if and only if A can be expressed Kn plus B, where K in n, K in z mean integers, and if A is not identically equal to B under modulo n, mean n does not divide A minus B, if and only if A not equal to Kn plus B, where K in z. So, next definition, if A is identically equal to B under modulo n, then B is called the residue of A under modulo n, and B lies between 0 to m minus 1, then B is called the least non-negative residue of modulo n. So, this way we can express what congruences of one numbers in terms of the another number, and keep it in mind so that we can discuss the further definition and problems. Now, we have make a note that it is a common, particularly in computer programs, to denote the least non-negative residues of the modulo n by A mod n. Thus, A is identically equal to B under modulo n if and only if A modulo n equal to B modulo n. Of course, A is not identically equal to B under modulo n if and only if A modulo n not equal to B modulo n. Next note, it is common particularly in computer programs to denote the least non-negative residue of A under modulo n by A modulo n. Thus, A is identically equal to B under modulo n if and only if A mod n equal to B mod n. Of course, A is not identically equal to B under modulo n if and only if A modulo n not equal to B modulo n. So, this way we can denote congruence of one number to the another number. For example, the following are some examples of congruences or incongruence. You take 35 divided by 12, the remainder is 11, therefore 3 and 11 are congruent to one another. Even if you divide 11 divided by 12, the remainder is the same thing we can do that. So, since 12 divides 35 minus 11, other way we can write subtract 35 and 11 and check it out the remainder and divide by 12, it exactly divides, therefore 35 and 11 are congruent to one another. And if you replace instead of 11 as a 12 and replace 12 by 11, therefore 35 is not identically equal to 12 under modulo 11 because 11 does not divide 35 minus 12. Similarly, 35 divides 11 you take it and 2 under modulo 11 you take it, so that it pakka identical to one another and subtract them. 35 minus 2 you check it out the remainder, and if it divides then one is congruent to another. So, this way we can write one number in terms of the another number of the congruences, and we can write the corresponding expression. Now, we have a theorem. I hope many of you know about that basic ideas of equivalence relation. It is applicable in congruences. Equivalence relation mean a set R you take it, it is said to be equivalence relation. Then number 1, it is a reflexive. Number 2, a symmetry. Number 3, transitivity. So, reflexive mean x related to x. Symmetry mean x related to y implies y related to x. Transitivity mean x related to y related to z, then x related to z. If it satisfies these three conditions, then it is said to be equivalence relation. Keep it in mind this. Let us go to theorem. Let n be a positive integers, then the congruence modulo n is reflexive. In terms of the congruences, A is congruent to A under modulo n for all A in Z. For symmetry, if A is identically equal to B under modulo n, then B is identically equal to A under modulo n for all A comma B in Z. For transitivity, if A is identically equal to B under modulo n and B is identically equal to C under modulo n, obviously A is identically equal to C under modulo n for all A comma B comma C in Z. So, this is the statement of the theorem. Now, we are going to discuss deeply. So, keep it in mind this, let us start with the proof. For any integer A, we have A into 0n plus A we can write, am I correct? So, hence 0n is 0, 0 plus A is A, therefore, A is identically equal to A under modulo n. For any integer A and B, if A is identically equal to B under modulo n, and A can be expressed as Kn plus B, because any congruence modulo can be expressed as a linear relation, therefore, A plus Kn plus B for some integer, and we can write a shift to A to B, therefore, B equal to A minus Kn, and then this can be expressed as minus K into n plus A. So, this implies B is identically equal to A under modulo n, since minus K is an integer. If A is identically equal to B under modulo n and B is identically equal to C under modulo n, then A can be expressed k1 into n plus B and B can be expressed k2 n plus C. So, we have A can be expressed k1 n plus k2 n plus C, therefore, add them k1 plus k2 into n plus C. Therefore, k1 k2 as k dash, therefore, it is a constant, therefore, constant into n plus C, obviously what A is identically equal to C under modulo n, since k dash an integer. So, this way we can prove the congruence relation also satisfies equivalence relation. Next we will go to definition. 1.6.4 says that if x is identically equal to A under modulo A n, then A is called the residue of x under modulo n. The residue class of A modulo n denoted by box A of suffix n, or just box A if no confusion will be caused. So, is the set of all those integer that are congruent to a modulo n. So, that is congruence of that is integer modulo n says that x such that x in z, where x is identically equal to A under modulo n, or rather we can write A plus k n where k belongs to z. So, note that writing A in box B n is same as writing A is identically equal to B under modulo n. So, for example, let n equal to 5. There are 5 residues of modulo 5, namely the sets integer modulo 5 of 0 is. So, these are all the numbers. If you take this number divided by 5, the remainder is 0. Therefore, 0 convert to 0, 5 divided by 5 is 0, therefore, 5 it is equivalent to 5. 0 is congruent to 5, 0 is congruent to 10, 0 is congruent to 15, congruent to 20, like that it will come. So, the technique is, so you take a number, that number divided by 5, find the remainder, and the remainder is 0, then 0 is identically equal to this. So, it is very easiest example that the integer modulo numbers. Similarly, the 1 you take it and take a number 6 divided by 5, remainder is 1, therefore, it is equivalent to 1. You take the 4 minus 4 and then remainder you take it, 1 will come. So, that minus 4 minus 9 minus 14 divided by 5, the remainder is 1. Similarly, 6, 11, 16, 21 and so on, you take it divided by 5, the remainder is 1, therefore, the 1 is congruent to these numbers. Similarly, 2 is congruent to 2, and then 7 divided by 5 you take it, and then a remainder is 2, therefore, 7 is congruent to 2, 12 is congruent to 2, and minus 3 is congruent to 2 and so on. So, we can write in terms of the roster form of set built roster form of the set notation that 2 under congruence 5 can be written like this. Similarly, you go to 3 and then congruence of 5 is 3, and then 8 divided by 5 is 3, 13 divided by 5 is 3 and so on. So, it goes like that. Similarly, you take a number 4, 4 is congruent to 5 is 4, and 9 by 4 is 9 by 5 is equal to 4, therefore, 9 is congruent to 4, minus 1 is congruent to 4 and so on. So, this way we can express the congruence relation. Next example, in residue classes modulo 2, the integer modulo 2 is the set of all even integer, and then congruence of 2 is the set of all odd integers. Say for example, you take 0 under modulo 2, 0, 2 divided by 2 remainder is 0, therefore, 2 is congruent to 0 and 0 is congruent to 2 and 0 is congruent to 4, 0 is congruent to 6, because 4 minus 0 is 4 divided by 2 is 0, therefore, they are congruent to one another. Similarly, we go for our 1 under modulo 2, therefore, 1 is congruent to 1 and then 1 is congruent to 3, 1 is congruence to phi and so on. So, these are all the ways we can do for the congruences. For example, the congruence modulo phi, we have 9 under congruence phi can be expressed 9 plus phi k, where k in z. This can be expressed 9 plus or minus phi. You take either direction, positive direction as well as negative direction, you take it. 9 plus phi is 14, 14 under modulo phi is 4, 9 minus phi is 4, 4 divided by phi under identically equal to this is 1. So, this way we can express 4 is identically equal to phi is 4, right. Therefore, this can be expressed in terms of 9 plus phi k, where k in z. Similarly, we can express the values of this one as minus 1, 4, minus 6, 9, 14 and so on, like that. So, this way we can write corresponding set values of congruence of 9 under modulo 5. So, we also have 4 congruence phi as 4 plus phi k, where k in z, 4, 4 plus or minus phi and so on we have. So, that the corresponding set values is minus 11, minus 6, minus 1, 4, 9, 14, 19, 24 and so on. Clearly, the congruence, that is 4 congruent under modulo phi is equivalent to 9 under modulo phi. So, this way we can do with the help of the residue classes, rather it is called integer modulo. So, it is the easiest way to express the congruences. Next, if x is identically equal to a under modulo n, and a lies between 0 to n minus 1, and a is called the least non-negative residue of x under modulo n, because we do not know what the value of x. And then if you find out this technique, or if you apply this technique, then you can easily write the corresponding values of x under modulo a, or rather x minus a, by n is equal to k, then x equal to a plus nk in terms of the equations. So, it comes under the linear Diffie equation. We can determine the value of x. For example, if you take n equal to 7, there are 7 residue classes under modulo 7. In each of these 7 residue classes, there is exactly one least residue of x under modulo 7. So, the complete set of all least residue of x under modulo 7 is 0, 1, 2, 3, 4, 5, 6, 7. So, you can apply in a Cayley table, and future we can study the group theory, so that you can understand further what the Cayley table of this. So, like that you can extend to 3, 4, 5, 6, 7, and similarly 0, 1, 2, 3, 4, 5, 6, 7, 7 does not come because it is integer modulo 7. Therefore, for example, if you take 4 plus 4, that is 16, 4 plus 4 is 8, 8 by 7, therefore, remainder is 1, therefore, corresponding value is 1. 4 plus 5 is 9, right. So, 9 under modulo 7 is 2. So, like that we can easily calculate with the help of the Cayley table. Now, let n equal to 7, there are 7 residue classes under modulo 7, and then we have a set of least residue of x is 0, 1, 2, 3, 4, 5, 6. We have a definition, the set of all residue classes under modulo 7 often denoted by z divides n z, which is equal to the class A n, where A lies between 0 to n minus 1. So, one often sees the definition of z divides n z equal to 0 to n minus 1, because n numbers, if you start with 0 totally n minus 1, 0 to n minus 1, then n number is there. So, which should be read as equivalent to the previous ideas, that z divides n z, with the understanding that 0 represent 0 under modulo n, 1 represent 1 modulo n, 2 represent 2 modulo n, and so on. Each class is the represented by its least non-negative residue, but underlining the residue classes must be kept in mind. For example, a reference to minus a as a member of Z under modulo Z reference to n minus a under modulo n, provided n greater equal to a and minus a is identically equal to n minus a under modulo n. Next we will go to the theorem. Let n be a positive integer, then we have integer modulo a is equivalent to integer modulo b n if and only if a is identically equal to b under modulo n. This is the statement we have to prove, and two residue classes under modulo n are either disjoint or identical, and there are exactly n distinct residue classes under modulo n, namely 0, 1, 2, 3 and so on n minus 1, and they contain all of the integers. Now we have a proof. If a is identically equal to b under modulo n, it follows from the transitivity property of congruences that an integer is congruent to a modulo n if and only if it is congruent to b under modulo n. So that the congruence of a, the integer modulo a is equivalent to integer modulo b. Therefore, this proves the converse. Suppose integer modulo a and b are equal, because a in integer modulo a in integer modulo b, so that a is identically equal to b under modulo n is true. And for the proof of 2, suppose the integer modulo a and integer modulo b have a common element c, and c is identically equal to a under modulo n, and c is identically equal to b under modulo n is also true. From the virtue of symmetry and the transitivity property of congruences, it follows that symmetry says that a is identically equal to b and b is identical to a. Therefore, a is identical to b under modulo n. The part 1 of the theorem follows, and it follows that congruence a and congruence b n also true. So, either congruence a and congruence b are either disjoint or identical. So, if a is an integer, we can divide a by n to get a can be expressed the linear expression k cube plus r division algorithm. Therefore, 0 less than or equal to r less than k. Thus, a is identically equal to r under modulo n, so that the congruent, that is integer modulo a and integer modulo r are equal. This implies that a is one of the residue classes of integer modulo 0, 1, 2, 3 and so on n minus 1, because the integers 0 to n minus 1 are incongruent under modulo n. It follows that there are exactly n residue classes of modulo n. So, this way we can prove that this theorem. In continuation of the congruent and incongruence, let us go to discuss the complete system of residue. Let n be a positive integer and a set of integers a1, a2 and so on an are called a complete system of residue under modulo n if the set contains exactly one element from each residue classes under modulo n. For example, you take n equal to 4. So, what happen? Then the class of 4, we have a what under modulo 4, the complete residue of 4 minus 12 and 9 minus 6 and minus 1 is a complete system of the residue under modulo 4, since minus 12 belongs to integer modulo 0, 9 belongs to 1 and minus 6 belongs to class 2 and minus 1 belongs to class 3, because the number 4 you take 12 divided by 4 is remainder 0. You take a number of 9 and divided by 4, you have a remainder is 1. You take 6, the remainder is 2, and you take a number minus 1 and then remainder you check it out 3, and therefore it belongs to what 0, class 1, class 2, class 3. So, of course, it can be easily verified that 12 minus 7, 18 minus 19 is another complete system of the residue modulo 4. So, it is clear that the simplest complete system of residue under modulo 4 is what 0, 1, 2, 3. So, the set of all non-negative least residue of modulo 4 can be generated. Another example, let n equal to 7 you take it. So, we have a complete system of residue in terms of the expression x, start with x, then x plus 3, x plus 3 square, x plus 3 cube plus x plus 3 power 4, x plus 3 power 5 plus x plus 3 power 6, like that. So, it is a complete system of residue under modulo 7. You take x belongs to integer. To see this, let us first calculate the value of the power of 3 under modulo 7. We start with 3, 3 under modulo 7, 3. Now, you go to the 3 square. 3 square is 9, 9 divided by 7, remainder is 2. Therefore, 3 square is identically equal to 2. And you take 3 cube is 27, under modulo 7 you take it, it becomes 6, and then 3 power 4 is 3 cube into 3. So, it becomes 6 into 3 is 18 under modulo 7, then remainder is 4. So, we have 3 power 5, 3 power 5 can be expressed 3 cube into 3 square. So, we have 12 under modulo 7 is 5, and 3 power 6 as 3 cube into 3 cube is 6, 6 into 6 is 36 under modulo 7 is 1 will come. So, that we can write one number in terms of the another number in terms of the modulo. So, therefore, the result follows for x equal to 0 you put it, in general result follows that immediately since x plus 3I and minus of x plus 3j. So, that we have 3I minus 3j. So, this way we can express in terms of unknown variable, and then we can bring to the help of congruence to the unknown variable. And next theorem says that let n be a positive integer and s a set of integer. S is a complete system of residue under modulo 7 if and only if S contains n element and no two elements of S are congruent under modulo n. So, this way we have to start with the congruences of system residue modulo n. So, proof is if S is a complete system of residue, then two conditions are satisfied. To prove the converse, we note that if no two elements of S are congruent, the elements of S are in different residue classes under modulo n. Since S has n elements, so all the residue classes must be represented among the elements of S. Thus, S is a complete system of residue under modulo n. So, this way we can prove the first statement of the theorem and followed with other. Now, definition we say that the congruence in terms of the integer modulo n, or rather it is called as a residue class under modulo n. We say that the residue class n of A is relatively prime to n. Relatively means the greatest common divisor of two number is 1, and then if each element of residue class A is relatively prime to n. For example, if you take n equal to 10, then 10 residue classes under modulo 10 are, for example, residue class of 0 under modulo 10, you take 0 under modulo 10 is 0, you take a 10, 10 divided by 10, the remainder is 0, therefore equivalent to 0, 20, 30, minus 10, minus 20, minus 30, all are divided by 10 is equivalent to no remainder, therefore 0 is equivalent, therefore 0 is equivalent to these numbers. Similarly, you take 1 under modulo 10, it become 1, and 11 you take it divided by 10, the remainder is 1, and then 21 you take it divided by 10, remainder is also 1, 31 remainder is 1, and so on. So, that we have the congruence relation of 1 under modulo 10 is minus 29, minus 19, minus 9, 1, 11, 21, 31 and so on. Similarly, go for 2 under modulo 10 and then we have like that. 3 under modulo 10, then the number is 3, and 13 divided by 10 remainder is 3, 23 divided by 10 remainder is 3, 33 divided by 10 remainder is 3, minus 7 divided by 3 is remainder is 3, and then you have to go to the backtrack of negative sign, minus 17 divided by 10 the remainder is 3, so that it goes like that. So, in this way we can find out the the residue classes of 4, 5, 6, 7, 8, 9, 10, the corresponding the values that is equivalent to congruence of to one number to the another number. So, clearly the residue class 1, residue class 3, residue class 7 and residue class 9 are relatively prime to 10. So, 1 and 3 you take GCD is 1, 3 and 7 GCD is 1, 7 and 9 the GCD is 1, like that. So, we can incorporate it with relatively prime of one number to the another number in terms of residue classes. Now, we have a proportion if a residue class under modulo n has one element which is relatively prime to n. Relatively prime to n means the GCD of one number to the another number is 1, then every element in that residue class is relatively prime to n. So, next we have a proportion if n is a prime, prime is a number divisible by itself and 1, then every residue class under modulo n of residue class 0 n is relatively prime to n. So, if the number is also prime and defaultly it will come. So, except the class 0 you take it, everything it will comes like residue classes of relatively prime to one another. Next we have a definition, let n be a positive integer, then the Tottian function phi of n is a number of residue classes of modulo n which is relatively prime to n. A set of integers a1, a2 and so on, a of phi n is called a reduced system of residues. If the set contains exactly one element from each residue classes under modulo n which is relatively prime to n. For example, we have come across 1.69 and then 1.69, we have class 1, class 3, class 7, class 9 under modulo 10 are residue classes that are relatively prime to 10. So, by choosing minus 29 from class 1 of base modulo 10, minus 17 from class 3 base 10, 17 from 7 base 10, 39 from 9 base 10. So, we get the reduced system of residue classes 10 is minus 29, minus 17, 17, 39 will come. Similarly, 31, 3, minus 23, minus 1 is another reduced system of residue class under modulo 10. So, that we can understand what is the meaning of reduced system of residue classes. Now, we have a theorem based on that in terms of the Tottian function and reduce residue system and relatively prime of one number to the another. Let m be a positive integers and s is a set of integers, then the reduced system of residue classes is if and only if S contain exactly phi of n elements, no two elements of S are congruent under modulo n and each element of S is relatively prime to n. So, this is the statement of the theorem and we have a proof. It is obvious that reduced residue system satisfy the three conditions. To prove the converse, we suppose that S is a set of integers having three properties because no two elements of S are congruent. So, the elements are in different residue modulo n. Since the elements of S are relatively prime to n, there are the residue classes that are relatively prime to n. Thus, phi of n elements of S are distributed among the Tottian function phi of n, and this is the residue classes that are relatively prime to n, and in each residue classes there it satisfies. Therefore, S is the reduced system of residue classes under modulo M. Now, we have a definition. If two integer x and y you take it, they are multiplicative inverses. If we have a equation x y equal to 1, identically equal to 1 under modulo n, where n is a positive integer greater than 1. See, we have a more general form here to be determined the value of x and y. If this value is identically equal to 1, because one is the inverse of the other only we can get it. So, other way we can write in terms of the congruences of two integer x and y or multiplicative inverses if the product of these two numbers identically equal to 1 under modulo n, where n is a positive integer which is greater than 1. So, we have a clear picture about the table choosing x value, and then you take the modulo n, and then we can easily find out the inverse of each value. So, let us start. Y does not always exist. Clearly, we have a given x and n. Under modulo n equal to 13, you take it, check it out. The n should be the prime. Here n equal to 13, 13 is a prime. The following table gives all the possibilities values of the multiplication inverses y equal to 1 by x we can write. You start with the x equal to 1, you take it, then what happen? Y equal to 1 by 1 under modulo 13. Suppose you take x equal to 2, right, you have to take the modulo 13, what happen? Say the value is 7, right, because you have to take the division of one another. Under modulo 2 you take it, so under modulo 13 you take it, right. So, we have a 7. So, 7 into 2 you take it. For example, xy equal to 7 into 2 you take it, it becomes 14. 14 under modulo 13 you take it, it's pakka, it works what identically equal to 1. So, like that you have to check it out. So, what you have to do is you check the value of the numbers 1 to 11, you have 0 to 11 you have to take it, or 1 to 12 you take it, and then 1 by 1 you check it out, so that you can easily understand the beauty of which one is the inverse of the other. Suppose you take 3, right. So, what happened? X equal to 3. So, 3y is identically equal to 1 under modulo 12 you take it. So, what value of y you substitute so that the value will become 1. For example, you start with number y equal to 1, 2, 3 and so on. So, if you take number 9 you take it. So, if you know strong table of 12, so that easily can understand the beauty of the inverse of the other. If you take 9, then it becomes 27. So, under modulo 12, 3 times of 12 is 26, therefore, and 3 into 9 equal to what 27. 27 divided by 12 you take it. So, the remainder is what? So, how many times 12? So, we have to take corresponding 2 times of 12 is 24, the remainder is 3. Therefore, we have what? The remainder is 3, therefore, what? 3 in a corresponding inverse is 9, or 9 is the inverse of 3. So, like that you have to apply the division algorithm, and you take one value and we can find the another value. So, x y identically equal to 1 under modulo n we can do in terms of 4 into 10 identical 40, 40 divided by 12 exactly identically equal to 1 will come. So, this way we can do that the corresponding inverse of one number to the another number. Similarly, for 5 we have a inverse 8, for 6 we have a inverse 11, and 7 we have a inverse 2, 8 we have a inverse 5, 9 we have inverse 3, 10 we have inverse 4, 11 as inverse 6, and 12 inverse is 12. So, 12 into 12 is 120, 144 divided by 12, right. So, that Pakka it will come remainder. So, this will have the number, one number in terms of another number inverse can get it using the congruences. This means that the division in integer modulo 13 are always possible and unique. So, the multiplicative inverse y of x is z over 13z do always exist and are unique. On the other hand, if you take n equal to 14, now n now is composite, then for x equal to 1, 2, 3 and so on 13, some values of y equal to 1 by x under modulo 14 exist, whereas the other do not. So, you take x and y, the inverse of 1 is 1, and here does not exist 2, 3 having the 5, 5 having 3, and then 9 having 11, and 10 does not 11, 9, and then 13 having like that. So, this way also we can find out the inverse of one number where n is a composite. Previously we checked for n is prime, therefore, beautifully it will come the remainder, whereas composites sometimes may get it, sometimes may not get it. So, this means that only the numbers 1, 3, 5, 9, 11 and 13 have a multiplicative inverse under modulo 14, or equivalently only the those divisors by 1, 2, 1, 3, 5, 9, 11 and 13 modulo 14 are possible. So, this observation leads the following the results. They are the multiplicative inverse 1 by b under modulo n exists if and only if the GCD of b comma n equal to 1. Now, by corollary says that there are phi of n numbers b for which 1 by b under modulo n exists. For example, you take n equal to 21, since the Tottian function phi of 21 equal to 12, because the number of divisors of 21 you take it, and then phi of 21 will get it. There are 12 b for which 1 by b under modulo 21 exists. So, this way we can incorporate it what a multiplicative inverse in terms of the Tottian function. So, in fact, the multiplicative inverse under modulo 21 only exists for the following table b. So, you take the value of b from 1, 2, 4, 5, 8, 10, 11, 13, 16, 17, 19, 20 corresponding the modulo of this one is 1, right. So, phi of 2, that is b, you take it 2, therefore, the inverse of b is 11 under modulo 21, right. And similarly, you take a 4, we have 16, 5 we have a 17, 8 having 18, 9, 10 having 19, 11 having 12 and 13 having 3, 13, 16 having 4, 17 having 5, 19 having 10 and 20 having 20. So, this way we can find out the multiplicative inverse under modulo 21. Now, we have a corollary, the division A divides B under modulo n. Assume that A divides B is lowest terms is possible if and only if 1 by B that is inverse value of one number to the another 1 by B modulo exists. So, if and only if the GCD of two number equal to 1. So, compute 6 divides B under modulo 21 whenever it is possible by multiplicative inverse of 1 by B modulo. In the previous table, we just need to calculate 6 into 1 by B under modulo 21. So, you take B equal to 6. So, what happened? 6 by 6 that remained 1, right. So, we have a b equal to 3, 6 by 3 is 2, right. So, you substitute b into 1 by 2, it will come. If you take b equal to 4, then it becomes 12, or b substitute 12, right, 6 by b, right, you take 12, so that you can get the value of under modulo is corresponding 4 is coming C, right. So, like that you can substitute the value of b equal to 5, we have a 18, and then 8 having 6, 10 having 9, 11 having 12, 13 having 15, 16 having 3, and then 17 having 9, and then 10 having 19, 19 having 18, and 20 having 15. Like that you can get the value of b corresponding to inverse of b. So, find 1 by 154 under modulo 81 and 4 by 154 under modulo 81. So, you have to following the solution. So, 1 by a under modulo n is equal to x you consider. Therefore, a into x is identically equal to 1 under modulo n. So, this can be expressed as ax minus ny equal to 1. This is a linear Diophantine equation. We only need to find x and y in 154x minus 81y equal to 1. So, already I explained how to solve. Once again we will see the solution to this one. To do, we first the Euclid algorithm to find the GCD of two number 154 and 801. Now, which one is a bigger? 801 is bigger than 154, therefore divide 801 by 154. So, 801 can be expressed 154 into 5 plus 31, and then 154 can be expressed 31 into 4 plus 30, and the comparative study with 31 and 30, 31 is bigger than 30, therefore 31 divided by 30, 31 can be expressed 30 into 1 plus 1, and then 30 can be expressed 10 into 3 plus 0. So, this way we can express the linear Diophantine equation. Since the GCD of this number is 1, therefore, according to this theorem 154x minus 801y equal to 1 is solvable, because the GCD of this is exists. So, we now write to backtrack of the result. From this 31 can be expressed as 801 minus 154 into 5, and 30 can be expressed 154 minus 31 into 4, and 1 can be expressed 31 minus 30 into 1. So, and you go to backtrack, 1 can be expressed 31 minus 30 into 1. So, 31 minus this can be expressed as 154 minus 31 into 4 into 1. Therefore, 31 minus 154 into 1 plus 4 into 31. Therefore, we have what? So, 31 as 5 times, right. So, 31 having 5 times, therefore, 5 into 31 minus 154, and 5 into 31 can be expressed 801 minus 154 into 5, and then multiply them. So, we have 154 having 26 times. So, for 5 into 801 minus 26 into 154. So, the expression can be written as what? 801 into 5 minus 154 into 26. From this we can infer that x is identically equal to minus 6, which is identically equal to 775 under modulo 81. Therefore, 1 by 154 having the modulo 81 as 775. So, this way we can find out the one number is the inverse of the other. Similarly, we can go with 4 divided by 154 in the same manner. We have 4 into 1 by 154 under modulo 81, then 4 by 154 is identically equal to 4 into 775, which is identically equal to 697 under modulo 801. So, based on that we have a theorem, the greatest common divisor of a comma n equal to d. If d does not divide b, then the linear congruence Ax identically equal to B under modulo n as no solution. So, if does not divide, then very difficult to find out the solution to this equation. So, we have to prove this theorem with the contrapositive of the assertions that Ax is identically equal to B under modulo n has a solution. Therefore, the GCD of A comma n divides B. Suppose that S is the solution, then we can write the linear expression in terms of the congruences. As is identically equal to B under modulo n, and we have formed the definition of the congruence that n divides As minus B, or from the definition of divisibility we can express As minus B is equal to Kn for some integer k. Since the greatest common is A comma m divides A and the greatest common is A comma m equal to Kn, it follows that the GCD of A comma m divides B. So, based on that theorem, we have let GCD of A comma n equal to D, then the linear congruence Ax is identically equal to B under modulo n as a solution if and only if D divides B. Now, we have a theorem, let GCD of A comma B equal to 1, the linear congruence Ax is identically equal to B under modulo n as exactly one solution. The proof is very simple. So, if you have a GCD of a number is 1, there exists x and y such that Ax plus by equal to 1 structure you have to write in terms of this Ax plus ny equal to 1 and multiplying both sides by b, so that Ax into b plus ny into b equal to 1. Therefore, we can write as A into xb plus n into yb equal to b. Seems to be that A into xb minus b is a multiple of n, or A into xb is identically equal to b under modulo n. So, the least residue of xb under modulo n is the solution of the linear congruence. So, this is the uniqueness of the solution that you can easily do the solution to the problem. Similarly, we have a theorem, let GCD of A comma n equal to D, and suppose D divides B, then the linear congruence Ax identically equal to B under modulo n as exactly D solution under modulo n. So, these are all given by let it be T plus n by D, right, because the division algorithm we have T plus n by D, T plus 2 n by D and so on, T plus D minus 1 into n by D value will come if you do the process of divisibility of n, and then T the solution, the unique modulo n by D as a linear congruence we have A by D into x is identically equal to B by D under modulo n by D. So, by theorem 1.612 the linear congruences has a solution since D divides B. Now, let T be such a solution, therefore, T plus k into n by D for k equal to 1 to D minus 1 are also solution, since A into T plus k into n by D is identically equal to At plus Kn into T by D, which is identically equal to At, which is identically equal to B under modulo n. So, we discussed the theorem 1.612. Now, we are going to discuss one example 1.615. Find the values of x of the equation 154x identically equal to 22 under modulo 803. Notice that this expression of 154x is identically equal to 22 under modulo 803 can be expressed as 154x minus 803y equal to 22, because 154x minus 22 divided by 803 is equal to some y you write. Therefore, 154 minus 154 into x minus 22 equal to 803 into y. Therefore, 154x minus 803y equal to 22. So, this way we can write the equation. Now, keep it in mind this we are going to solve the linear Differential equation. Now, we have to use the Euclid's algorithm to find the GCD of 154, 803 as follows, that 803 is equal to 154 into 5 plus 33, and 154 can be expressed 33 into 4 plus 22, because 32 and 122, compare them. 32 is greater than 122, therefore 33 can be expressed 22 into 1 plus 1, 11, and then 22 can be expressed 11 into 2 plus remainder is 0, therefore the GCD of these two number is equal to 11. So, keep it in mind, this the greatest common divisor of the two number, so that the problem is solvable. And then the GCD of 154, 803 equal to 11, and then 11 divides 22. Therefore, according to the theorem 1.612, the equation 154x minus 801y equal to 22 is solvable. Now, we write the above resulting equation as rewritten as 33 can be expressed as 803 minus 154 into 5, and 22 can be expressed 154 minus 33 into 4, and 11 can be expressed 32 minus 22 into 1. So, the work backwards on the above new equations, 11 equal to 33 minus 22 into 1, and then 33 minus 22 can be expressed 154 minus 33 into 4 into 1, and then multiply them. We have 33 minus 154 plus 4 into 33. The coefficient of 33 is 5 times minus 154, and then substitute 33 can be expressed 803 minus 154 into 5, and then multiply them. 5 into 803 minus 5 into 5 is 25, minus 1 is 26 into 154. Therefore, it can be expressed 803 into 5 minus 154 into 26. Therefore, 11 can be expressed as the linear Diophantine equation, what, 803 into 5 and 154 into 26. So, the values of x and y is determined with the help of this equation, x equal to 5 and y equal to 26. Therefore, x is identically equal to minus 26, which is identically equal to 777 under modulo 803. By theorem, there are in total 11 solution of 154x minus 805 equal to 22. So, we list all of as follows, and we can write the verification of the result on right. So, we can express 777 as 154 into 777, which is identically equal to 11 under modulo 803. Therefore, we can find the inverse of one another, and this can be expressed as 777 plus 803 plus by 11 equal to 47, identically equal to 47. Therefore, 154 into 47 is identically equal to 11 under modulo 803, and then 777 plus 3 into 803 by 11 equal to 1, identically equal to 193. Therefore, 154 into 193 is identically equal to 11 under modulo 803. Similarly, 777 plus 4 into 803 by 11 equal to 266. Therefore, 154 into 266 under modulo 11, modulo 803 is 11, identically equal to 11. Similarly, you go for 777 plus 5 into 803 by 11 equal to 339. Therefore, 154 into 339 identically equal to 11 under modulo 803. Similarly, 777 plus 6 into 803 by 11 identically equal to 412. Therefore, 154 into 412 is identically equal to 11 under modulo 803, and 777 plus 7 into 803 by 11 equal to 485. Therefore, 154 into 485 is identically equal to 11 under modulo 803. Then 777 plus 8 into 803 by 11 equal to 558. Then corresponding we have 154 into 485 identically equal to 11 under modulo 803. Similarly, for rest of them we can do like that. So, this way we can write the congruences in one in terms of the another. Thank you.